Okay, welcome back to the second Loeb lecture in our series. We're happy to have Asimina ARVANITAKI here. She's the Stavros Niarchos Foundation Aristarchus Chair in Theoretical Physics at the Perimeter Institute, and I'm not going to repeat all the rest of her biography, but you can read it on the announcement if you didn't hear it yesterday. And she's going to be telling us more about the cosmic neutrino background. Let me also add that if you have questions, we want people on Zoom to be able to hear them. Yesterday, people were complaining they didn't hear them. So if you have a question, feel free to ask during the talk, but then try to wait for me or Yolanta to bring you a microphone before you ask the question. Thanks.
So hi, everyone. So for today and tomorrow, I'll go more into detail about what I summarized essentially yesterday. And I will start by talking about what we did about the distribution of the Earth and going more to the nitty-gritty details of it. So, but before I do that, we need to set some sort of, let's call it kind of like ground rules. So why isn't this working? OK, now it's working. OK. So, so again, the cosmic neutrino background. It was created actually at the time, it decoupled from the expansion of the universe when the temperature was around a few MeV. There is a small difference in the decoupling temperature that has to do with the type of neutrino you have, if it's electron, muon, or tau neutrino. Okay, but that's a small correction to this. Now, because the decoupling, and that corresponds to a time where the universe was a fraction of a second old, because the decoupling happened when these neutrinos were relativistic, still relativistic. Their mass is much smaller than an MeV, mega eV temperature, okay? So because that happened, even today, they still follow a massless Fermi-Dirac distribution. So if you look at their momentum distributions, it looks like the mass doesn't matter. Okay? Which is very weird, because if you look at dark matter, for example, you have the Boltzmann factor, which goes like e to the minus p squared over 2m times the temperature. This is not true for neutrinos. So their distribution, in a way, is independent of their mass and independent of whether or not they're relativistic, so the distribution in momenta. Okay? And that is important for the dynamics. So it follows, so for all the averaging, for the average density that you will see, that's the relevant factor. F is 1 over e to the kt plus 1. The temperature, again, remember, is very small. It's 10 to the minus 40 eV, slightly smaller than the photon temperature of the CMB today. And the expectation is that you have neutrinos and antineutrinos, almost equal numbers, up to a factor of 10 to the 9. 1 part in 10 to the 9, sorry. Another important clarifications that didn't say yesterday is that the results that I'm talking about strictly apply when the neutrinos are Dirac, where you can define neutrinos and antineutrinos. There is another type of neutrino for those of you that are not so versed in particle physics, which is Majorana type. And basically, those are essentially, their state is an equal superposition of particle and antiparticle. So you cannot really define the same thing, neutrinos and antineutrinos. So it's like the particle Majorana neutrinos is like they are their own antiparticles, okay? And their dynamics is different, so I will not talk about those. The other thing I will assume, there is another subtlety. I will always be talking about electron neutrinos or antineutrinos, muon neutrinos or antineutrinos, and tau neutrinos or antineutrinos, meaning I will distinguish them and distinguish neutrinos basically based on their flavor or interaction properties. And that is not correct, because neutrinos today are actually stuck in their mass eigenstates. And these two things don't necessarily, these are two different bases that don't necessarily align. Okay? And that will introduce an error in the numbers that I will talk about, but it's order 1. So it won't change the conclusion significantly. So another important thing is the mass scale of these neutrinos. Yes?
Real quick, because it was
Yes.
up on the slide, and this question can be put off till the end, but are there any well-motivated beyond the standard model theories that would indicate a larger
Signal?
Asymmetry?
Well, not in my mind. I'm a minimalist in nature when it comes to this. I mean, we are theorists. We can come up with all sorts of crazy models. I mean, if you add enough bells and whistles, you can do it. For example, you would need something to decay to some scalar field, for example, that decays to neutrinos and not antineutrinos, for example, after neutrinos have decoupled from electrons and positrons, because before that, whatever you do, things redistribute themselves when they are in thermal contact. So you can do it, but I don't want to. And if I had to guess, nature doesn't like that either.
I was looking for more signal.
I know you're looking for more signal. I'm telling you, look, I mean, if you want, there could be dark matter that gives you bigger signal. So you can imagine dark matter candidates. That's a better way. I don't want to mess with the beauty of the minimalist CNUB. And that's a thing of beauty because, so let's talk about the mass, because that's an important factor now. So you have, so you can have, you have 3 mass eigenstates, as I said. In these pictures here, the different colors tell you what admixture that the different eigenstates have, electron, muon, or tau, neutrino. And there are 2 different types of hierarchies. So you can have the normal hierarchy, which you see on the left, where by M1, M2, and M3, usually people say M1 means that it's mostly electron neutrino, and then 3 means it's mostly the heavier flavors. So M2 is the one that's in the middle. And on the left, you see what the people call normal hierarchy. On the right, you see what people call inverted hierarchy, where it is the, basically you see that the electron neutrino, like in the standard model, the electron is the lightest lepton, and the tau is the heaviest. But here you see that the electron neutrino is heavy. So this is what mostly electron neutrino is heavy. So this is what they call the inverted hierarchy. So that what we don't really know the absolute scale. There is some constraint from cosmology. What we do know is from neutrino oscillations, we know the mass splittings. So there is the oscillations of neutrinos coming from the sun that measure the small mass splitting. And there's the oscillation of neutrinos in the atmosphere that measure the large mass splitting, okay? And the key point of this is that you see the different hierarchies and composition. The key point of this, notice that if I take the square root of the largest of the 2 mass splittings, delta m squared, it gives me a lower bound on the neutrino mass, on the heaviest neutrino mass. So if I take the square root of this 2 times 10 to the minus 3 eV squared, I get this number of 0.05 eV, which tells you that the heaviest neutrino has to be heavier than that if I make the lightest one massless, okay? So there is a lower bound on the neutrino mass coming from these measurements. Now, the other thing I will assume is that given that I know from data that at least one guy is heavier than 0.0 eV, which is much larger than the temperature of the CNUB, I know that there's going to be at least one neutrino that's non-relativistic today. And this is actually very important because it reveals another great property of these cosmic neutrinos. They are the only non-relativistic components of neutrinos we'll ever be able to make, significantly, by significant fraction. If you think about it, radioactivity produces very boosted neutrinos. The energy of the decay products is much higher than their mass. Supernova neutrinos, huge. Carlos's ice cube neutrinos are essentially train wrecks that just plow through everything. So this is the only non-relativistic component that the world has, which makes them quite special. Okay? So I told you that the heaviest one has to be between 0.05 eV. And the question is, what is the upper bound on the mass? And I think in the talk that I will give, we've taken optimistically, I think, the upper bound to be around 0.8 eV, which comes from the Catherine experiment. Okay? The Catherine experiment that tries to measure the neutrino mass from measuring the end point of the tritium decay. So tritium can go to helium-3 plus an antineutrino plus an electron. And if you measure very accurately the distribution of momentum, in principle, you can measure the masses of the decay products and fit to the, given that we know the electron mass and the helium mass, you can fit for the neutrino mass. So, so that ignores, that's actually, so this bound of 0.8 roughly, and it's also a combination of mixing angles and essentially ME. So this upper bound ignores cosmological constraints. Okay? So I kind of trust my cosmology friends, and I could say that if you take the, so cosmology measurements tell us about the sum of the neutrino masses. And the reason that happens is when neutrinos become non-relativistic, they change the gravitational potential where the CMB now, the cosmic microwave background photons move through. And you also have large-scale structure measurements, right? The combination of those tell you that the sum of the neutrino masses has to be less than roughly 0.2 or 0.1 eV, okay? So for me, the most reasonable range of the heaviest neutrino mass is somewhere between 0.05 eV and 0.1 to 0.2 eV. 0.8, I will show it in the plots, but I consider it an optimistic estimates. But I know people, there are some people, I don't care about cosmology. I think cosmology has taught us a lot, so. Anyway, so astrophysical observation. So since it's relativistic, we know it will obey the Schrödinger equation, okay? So that's the equation I will be dealing with. You have the first term, you have the kinetic term, and then you have the interaction potential, which, so the question is, what is this interaction potential? And this interaction potential comes from the interaction of neutrinos with a vector current of the electrons, for the particle physicist in the room. That means it happens with a number of weak charges that an atom has, okay? For electrons, it is slightly different than mu and tau. For electron neutrinos, it's slightly different than mu and tau neutrinos because electron neutrinos can interact with electrons also with the exchange of a W and a Z, while mu and tau neutrinos only interact with the exchange of the Z. So that's why you have two different coupling constants here. So you get different contributions. So if you interact with a Z boson, you only measure, the only charge you see is the number essentially of neutrons that the atom has. While in the other case, there is a more a weird combination, okay, for the electron neutrinos. And just to give you a rough, and raw matter again is the density of atoms in matter. The interaction energy, just to give you an idea, it's very small, 10 to the minus 14 eV versus the kinetic energy now of 10 to the minus 6 eV, which is true for, and I'm normalizing to mass of 0.1 eV for the neutrinos. And this tells you now that this is a small effect. This also tells you that, for example, if I look at solar neutrinos or any other type of neutrino, this small interaction energy does nothing unless you sit to a neutron star, right? So now let's solve the Schrödinger equation. So we solve the Schrödinger equation, and we assume that so we take a neutrino wave on energy E neutrino and momentum k, and we solve the Schrödinger equation, fixing the energy, and we find that inside material, the momentum needs to change. And in change, the square of the momentum changes by an amount of minus 2 mu u. Okay, that's simple kinematics, energy conservation. So again, as I said yesterday, the index of refraction changes how much the kinetic energy of these neutrinos changes inside the material. And if u is attractive, the index of refraction is larger than 1. If u is repulsive, is less than 1. And this is actually a summary of values, just now to give you an idea. So you can take the expectation value of m neutrino u over k squared and calculate some average event of refraction for the neutrino, for the C nu b, for different materials. So you see for water, silicon oxide, which is essentially rock or dirt. And you see here that as you make the atom heavier, bigger number of neutrons, bigger number of protons, the index of refraction goes up. And in fact, you see actually the best material is kind of gold, gives very nice numbers. Slightly expensive to build the whole structure that you manipulate neutrinos with, but you can use it perhaps for the detector. I mean, gold is something that has good properties in these things, okay? And the thing to remember is that delta nu, this quantity that are always this delta, will measure how much the index of refraction is different than 1, is always larger than 0 for lepton-antineutrinos and muon and tau neutrinos. So let's do quantum mechanics now. So I have neutrino wave incidence on the interface between two media. One is vacuum outside, and inside you have matter. Okay? In order to solve this problem, what do we do in quantum mechanics? We take the wave function, we match the value of the wave function on the boundary. We require that the value of the wave function is continuous, and we also require that the derivative of the wave function is continuous. So that relates the amplitude of the incoming wave to the reflected and outgoing wave. Okay? I think we all have done it in quantum mechanics. So when you take the ratio of the reflected wave amplitude B over A, you find that, in fact, it's only the momentum perpendicular to the surface that determines the dynamics. And that is just by energy conservation and translational invariance across the surface. Okay, so any momentum parallel to the surface does not change. An interesting thing is that if you take the square of that quantity, you will find, and if you remember from optics where you did reflectivity of two media, this gives you the reflection coefficient. Okay, ignoring polarization effects for light. Similar for the transmitted wave, the ratio of C over A gives you the transmittance. And again, it's only the momentum perpendicular to the surface that matters. An interesting thing is that Snell's law here, you can see arising if you impose translational invariance across the surface of the medium. So you get that K outside is equal to K parallel inside, and you get the relation between the incidence angle and the refractive angle of the wave. You can also get from energy conservation and this thing, you can also get the fact that the reflected angle is the same as the incidence angle. So all these optics apply, all these optics things that we learned in our textbooks apply to this case. And you can see them arising for energy conservation and the symmetries of the problem. The other thing that is great about this, you see that essentially theta initial and theta refracted are slightly different by the amount of which the index of refraction is different. So it tells you that refraction can give a kick, changes the direction of propagation. Okay? Now, the critical angle you get when the momentum inside, when the ray comes out parallel to the surface. So K perp, the perpendicular, the momentum perpendicular to the surface on the inside matter is 0. Or the refracted angle is, a sine of the refracted angle is 1. Basically, the C becomes parallel to the surface. And this happens when the incidence angle is pi over 2 close to the square root of minus 2 delta nu. So now you see that if you remember from optics that the critical angle is related to the square root of the index of refraction. And this is where the square root of G Fermi comes in. So the intuition that I presented yesterday about talking about the kinetic energy along the perpendicular direction be less than u, you can also get from optics consideration and this matching of when you solve the problem properly. Okay? And it can only happen when this delta nu is negative. Okay? This is when you only get reflection. So it only happens for electroneutrinos and muon and tau antineutrinos. And when that happens also, there is another thing that changes. The momentum perpendicular to the surface inside becomes imaginary. So you get this exponential decay. This is exactly the evanescent wave. So in order to calculate the asymmetry now, you have to take the neutrinos that are coming from the outside, integrate over their angle of incidence, and also integrate over the momentum, because what I described is for a monochromatic wave, but of course neutrinos are not monochromatic, they follow a thermal spectrum. So you do two types of integrals of this form, and the final answer looks like this. Okay? This is a plot that shows the distribution. So the blue line here is a numerical integration of the solution of the problem that I described before for outside the Earth and inside the Earth for a fixed neutrino mass of 0.1 eV. And the dashed line, actually the orange line, is a semi-analytic fit that you can do when you take the asymptotic behavior, when you take the value of the asymmetry sum over the boundary and the very far away regime. Okay? The key point here, because delta nu is 10 to the minus 8 or so, you see that the fractional asymmetry is of that size. And the gradient here is set on the inside, as you might expect, the fall off by the evanescent wave scale. There is a cute thing that happens, and this scale, I should have a -1 here, so there is a typo. This scale is roughly 3 meters for the surface of the Earth, for the density of the Earth. Now, the question I have is, why is there a decay outside? What determines the decay of the asymmetry outside? Can anyone guess? I mean, it's not an obvious guess, by the way. I have to see the calculation to guess it. Because the momentum perpendicular to there is no imaginary part of the momentum. There's no exponential decay. So what makes the signal decay this way? Okay, I'll say because it's not obvious at all, actually. It's not. So there's. No, okay, I'll come back. No, it's not. Okay? And what happens on the outside is the fact that when a wave reflects, it creates a standing wave with an incoming wave of itself. So on the surface is where all the standing wave for the different momenta add up coherently up to an overall phase. And on the outside, as you move away, the different standing waves start to decohere because they are different. They are spread over frequencies. Okay. So the outside actually is a funny thing that it comes from an interference effect. And the fact that they look symmetric, if you look closely, they don't really match the values. It's only an artifact of the limit that delta nu is very small. If delta nu was order 1, like in ordinary optics, this could be completely different. They would look completely different on both sides. So it's just an artifact, and I actually don't have a good understanding, actually, in the end, why they look so similar, even delta nu very small limit. But I know it comes from this interference effect that is, let's say, decoherence effect as you go away from the surface, which is kind of neat. Okay. So now, of course, as we discussed, this is the flat Earth. The Earth is not flat. Okay. And the other thing is that I should have what I presented for neutrinos coming from only one direction. I need to take neutrinos coming from all directions. And the reason that we felt it's okay to ignore them is the following. So let's treat the problem like a 1D problem. So for neutrinos that see a repulsion from the Earth, they get reflected because they don't have enough energy to go over the barrier. But the neutrinos that are not reflected, they actually get accelerated when they go through the Earth. They speed up. They have more, they oscillate faster, okay? For a sphere, what this means is that when a neutrino, electron neutrino, bounces off the Earth, the corresponding antineutrino, electron antineutrino, will bend in such a way that it always comes out from the Earth again if the Earth was a perfect sphere. So there are no rays. If you do geometric optics, you can do this for a perfect sphere and see that there are no rays that can come from the back and cancel your effect. Okay? And this is just from the fact that the Earth speeds up the type that cannot get reflected. And this is crucial. The key point is that these neutrinos have to come from the outside, get inside the Earth, and get reflected from the back of the surface. So, of course, though, the Earth, not only, it's not flat, we know it's curved, but it's not a perfect sphere either, okay? So it turns out that you have to worry, indeed, by Locusy homogeneities of the Earth. And we know that they have to be small. So, and this is where our intuition comes from telescopes. So this is a problem that people that build mirrors for telescopes, X-ray or optical telescope, have to deal with. How flat, how polished, how much do I have to polish my surface so that I don't have to affect the reflectivity of the surface? And turns out that the relevant scale is not the wavelength, okay? It is the, again, always K perp. It's the momentum change of the neutrino, because you cannot really localize the surface. When we do scattering or any sort of detection, we know that if I exchange a momentum delta p, I cannot localize that position to less than 1 over delta p. So in fact, naively you would say, oh, it has to be, they have to make the Earth flap to 1 millimeter, which is impossible. But in reality, it is the lambda critical scale. It's the evanescent wave scale that's the relevant scale. So this is roughly 3 meters. And makes our life a lot easier because the Earth has a lot of spots where it's pretty flat. And these are 2 extreme examples. So in Bolivia, there's the salt flats that are flatter than 1 meter over a range of 100 by 100 kilometers. In fact, satellites use them for calibration, which is really neat. My favorite place to do the experiments is the Maldives. That's pretty flat too. Slightly nice ambiance. So that's another thing that would work. So the question is, can you go, how flat do you need? And as John asked yesterday, we probably need at least a kilometer by kilometer to 10 kilometer size patch to be flat enough. And that is because that has to do with how far away the incoming of antineutrino rays come from the behind. So if it's flat enough, then what we say, we think holds. So there are spots enough in the Earth that we think satisfy the necessary requirements, okay? Now, having said that, we have not done the full simulation. I think the local distribution will ultimately depend on someone doing a proper simulation of the effect. So for example, I told you that on the outside, you get this gradient coming from interference effects. I think that can easily become bigger or much smaller. The evanescent wave scale is just penetration of the classical in the wave dynamics. But the outside, this interference pattern will most probably be affected. Okay, so yeah, I think the next step for this, beyond what we have done, which is just apply our intuition, is and use what I think are good arguments, is actually do a simulation of a realistic terrain, not just a perfect sphere, because at distances that what we care about, local inhomogeneities for the Earth will also be as important as the curvature of the Earth. Okay. And this is how we came up with this plot here. Again, as we change the mass between 0.05 eV and 0.8 eV here, as I said, this is very optimistic, and I think this is the most likely range of the effect. Okay? So now, as I said, this gives out from the no-go theorems. So if I have an interaction with a mass with n atoms, it will fill an interaction energy in the neutrino background of this form. So now, because the gradient of the density is non-zero, you can see the creative force. And I'll give you numbers, 10 to the minus 31 Newton. Okay? Just to give you an idea, the mass of a proton, the weight, okay, the weight of a proton is roughly 10 to the minus 26 Newton. The weight of a proton, one proton, like the force by which it's drawn towards the Earth, 10 to the minus 26. This is 5 orders of magnitude smaller. This is small, okay? And in all honesty, even my craziest dreams, I mean, experiments are like 1 billion times away from this. So it's still small, but now it's non-zero. Of course, there's the other effect that was always non-zero. And this is the atom interaction with, if you have a spin, it interacts with a neutrino, with a neutrino current, basically the flux of neutrinos as they go through. So there is interaction energy that depends on the relative velocity of the neutrinos times the spin of the atom. And this is an even a smaller number, okay? But it's still 10 to the 5 times larger than what was previously calculated 40 years ago. So this is 10 to the minus 36 Newton meters. This is a torque. It's just really small, okay? Okay, so the Earth is just, and the reason that, the reason ultimately why we wrote that paper is the Earth is there, so you get these things for free. You don't have to try. So the question is, can we do better? And this is where the diffraction grating comes in. So let's set some ground rules, though, to give you some idea of how our thinking went during this process. So first important fact. So when you build, the first intuition you have about doing this, I need to build a lens. And then you think about the way we think about photons, what you learned in your optics books. But that's not quite right. First of all, neutrinos are fermions, which means that we cannot compress them too much without running problems with Pauli's exclusion principle. So whatever you build, the so-called gain that they define for lenses, it will never be large enough. So whatever you build doesn't have to be perfect, okay? Does not have to be perfect. And this makes your life a lot easier. Other thing, if you try to build if you apply, there is the famous lens maker equation that tells you that the focal point of a thin lens is the aperture of the lens divided by n minus 1, the difference of the index of refraction from 1. So if you try to build a lens, you find that, well, the focal point is more than 10 kilometers away. So good luck trying to build a construction like that. That's another thing. So traditional optics thinking doesn't really work either. And the other thing that's not so obvious when we learn about optics is that photons, because they have such a large index of refraction when they go through matter, or even air, they don't have to travel a big distance, so that the differential of phase, meaning if you have a wave traveling in vacuum, it would acquire a phase k times the length of the distance it travels in the vacuum. In the material, it will acquire a phase k times the index of refractions times the length. So the differential phase for photons, because n is order 1 most of the time, it doesn't take a large distance inside material for the photons to acquire a different phase between outside and inside. For neutrinos, this phase differential is actually usually very small at length, unless you have more than ordered a few kilometers of material to go through, dense matter to go through. And we realize that this is actually quite, we think this is a secret assumption in many optical systems that you see, that actually the phase differential is much larger than 1. It's kind of like a WKB approximation thing. But for the neutrinos, it does not apply. So we wanted to restrict ourselves. OK, let's stick to the regime where K delta L is much less than 1, and try to consider structures that are 1 to 10 meters. OK, there is one other difference that I forgot to mention, and I didn't put it, I almost forgot. Neutrinos do not get absorbed. They plow through everything. It doesn't matter that they're non-relativistic. They do not get absorbed. With photons, right, you can take a piece of paper and you can, you can take a piece of paper and shield the light of the sun and watch the eclipse, right, on a carton box. So you cut off, there is a lot of absorption for photons. For neutrinos, everything just goes through everything. There is no way you can screen neutrinos and have like an opening and have a nice opening that's very clean and calculate your wave from that opening. Nope, you have to take into account that neutrinos would just go through everything. Okay? And this is how we kind of reach this structure that I showed you yesterday. So you take, as I said, these rods of length L on a radius of the sphere R, and turns out they have to be similar, and explain again why, and they have a width W. Remember, the key point of that is that neutrinos have a wavelength between 2 and 4 millimeters. So now let's look again at the Schrödinger equation and understand better what happens when a neutrino wave goes through one with these rods. So you have the Schrödinger equation. If you substitute for the energy, you can rewrite the Schrödinger equation essentially like a wave equation for neutrinos. So you have grad square psi plus 1 plus delta nu square, k nu square psi is equal to 0. And you take that equation and you do the following. So you have a wave that is incident, again, parallel to the stick. And you want to see what happens at the end of the stick right here. So what you do now is you want to separate, because now, as I said, the phase that the wave accumulates inside is not much different than the wave accumulates outside. So you can separate. You can take out the fast oscillating component of the wave and you can rewrite this wave equation up here like this. So you have this I psi tilde, for this psi tilde, factorizing this e to the minus ikz, the normal propagation factor. And what you see, guys, is kind of something interesting. This still looks again like a Schrödinger equation. So, but what you have now is z, the direction of propagation, plays the role of time, okay? And k plays the role of the mass. So, and now this k delta nu is like the potential. And now you can understand the Schrödinger equation like its dual role, like a dispersion equation, okay? So you can do this, and then you can even do a further substitution where you write this psi nu tilde, this slow varying component, as e to the minus kf. And you see that the first term in f is just the phase that you accumulate. This first correction in f naught is just delta nu times the length you transverse inside the material. And then there's a second order correction that comes from dispersive effects. Okay, this is like a dispersion term. So it means that this F1 tells you that the wave kind of like spreads out a little bit, and it can also be imaginary. So there is amplitude modulation as well. You don't only have phase modulation. Okay, so this F now can have a small imaginary part. But if you do this, you still find that the neutrino wave still acts like the stick still acts like a phase diffractor. So this is what you get. This is the size of the this is the exponential of the e to the minus ikf. This is kf here that you plot in this axis as a function of the distance from the center of the stick. So this orange thing is what you get is if you assume that the stick just plays the role of a phase diffractor. Basically, you just take into account that the wave just accumulated phase inside the stick. And the solid blue line is the actual solution. So what this teaches you is that even though there are dispersive terms, they are not important. You can just ignore them. Turns out they only make, in the wave, they make like a 10 to 20% correction. In the final answer, it's slightly bigger, but it's still within the things that we can, it's still a good approximation to take the stick as a phase gradient, that it just imparts a phase. But in reality, when you simulate the whole thing, you need to take all these dispersive effects into account. In fact, it's very funny that this equation actually has a name. It's called the Fock-Leodonovich equation. And this is something that people use, for example, in beam optics. And by the way, we found it in X-ray optics too. This is how we learned about it. And now we come again to this. So we have the neutrino, the neutrino, we have the stick. There is a wave coming onto it. And I hope I explained to you why this is a very good approximation. So you can treat the neutrino wave. We cannot ignore the waves. The neutrinos come everywhere. There is no dark screen. So there is the plane wave outside the stick. And on the surface of the stick, there is just this, this phase factor. Okay? So now the question we want to ask is, what is the value of the field at the distance d? And the way we do this is we have to go back to 19th century optics. So Kirchhoff in the 19th century said that if you have the wave equation, you can actually, and you know the value of the field in a closed surface, you can calculate the value of the field in any point inside the surface. I won't write the formula because there is a nice intuition for that formula that Huygens developed some 2 centuries before Kirchhoff. So the reason that you can calculate the wave anywhere inside the closed surface is because you can treat the points on the closed surface as sources of spherical waves. And this is actually, and Kirchhoff is something that he calculated mathematically, but Huygens is something that he first came up with this idea that a wavefront you can separate in wavelengths and treat each point of the wavefront as a source. And the amazing part about it, he was kind of, let's call it an intellectual fight with Newton, because Newton thought that waves, photons were particles, while Huygens thought they were waves. And I think he got this intuition. I think I heard, I'm not sure if this is true, that he knew that, for example, that sound waves go around corners. So the great thing about Huygens is that in the 17th century, he came up with something that Kirchhoff proved mathematically 200, based purely on intuition alone. Okay? So he didn't have to know how to solve the equation. He understood what the solution of the equation was, just from pure intuition, which is amazing. We always think that older physicists, what did they know? I mean, these are some pretty amazing people. And the reason that what he was missing, turns out, is there is a funny angle factor. There's a product of, there is some sum of cosines that he was missing out. That's why his proof was not exact. So that took a while to get right, which is really cool. So, so when you do that, so when you take now the wave that you have at the end of the stick, and take the assumption that you have a small phase accumulated as the wave propagates inside the stick, and you also take the limit that the width of the stick and any distance that you deviate away from axis in this point is small compared to the distance, which is ZD here. This is the wave you get, okay? This is the plane wave part. You still have a plane wave, and you got a part that's proportional to the index of refraction. And there is another funny integral here, which I don't know how much, so there's the plane wave part. And actually, if one can recognize this part of the integral as the amplitude of a wave emitted from an opening. So if I were to do the same exercise and calculate the amplitude of a wave, if I have a hole in a dark screen for light, and I calculate the amplitude of a wave a certain distance away, making these assumptions here that the width of the opening and the distance at which I travel from the center is small, I get exactly the same answer. So this is the diffraction part. It's like a wave diffracting from the opening of the aperture of the rod. And what you do next is you take a wave that has a momentum k, but has an index of refraction larger than 1, and one that has exactly the opposite one, so to calculate the difference of neutrinos and antineutrinos. And you take the square. Now, because in the amplitude there was the plane wave term and a term that was proportional to delta, it is the plane wave term interfering with a term proportional to delta to give you again an effect linear in delta, not delta squared, which is very important. And this is the shape that you get for a monochromatic wave a certain distance away. And this distance has to be now, if you want the wave fronts, the wavelets that are emitted from the front of the stick to add up coherently, you have to be at a point that's a distance w squared of the lambda neutrino away. And actually, I think this is where I will stop for tomorrow. I think this is a good place to stop. So the key point about this is that the rod is a neutrino phase diffractor. And you can get a lot of intuition about what happens to this wave as it goes through the stick from the opening, from what you know from a plane wave hitting a dark screen with an opening. Another thing to keep in mind is that the size of this asymmetry drops like linearly with a distance beyond the optimal point here. And the width also increases like the square root of the distance from the screen, from the front of the stick. For this is the dynamics, okay? And again, this is stuff that I showed you yesterday. Now I hope you better understand how this picture came about. This is just a diffraction pattern. In reality, we're not really focusing the neutrinos, we're just scattering them from the stick. It's just a pure diffraction, pure diffractive effect. And what the stick does, it separates neutrinos and antineutrinos differently because they see exactly opposite potentials. So you see that in the beginning you have, I mean, I don't plot it here for the parameters I have, this corresponds to 2 meters. Below here you have no asymmetry. You see that the first spot where the big asymmetry appears for the parameters that I was using appears in W squared over lambda. And the size is of order delta. And you always get excess of the things that are attracted to the stick. Always. And this is the other pattern. So these are basically diffraction patterns, okay? Yeah, I think before I go and explain to you the rest, I think this is a good time to stop for tomorrow. And I would like to take your questions now. So tomorrow we'll discuss the full big sea-urchin, how it comes about, okay? Good, thank you guys. Any questions? Yes?
Just a quick question. What's the end sort of like plot? Like, do you get an energy distribute, like a spectrum of neutrinos, or?
Yes, the neutrino spectrum is given by this Fermi Dirac distribution. And I'm not switching the screen from the Zoom people. So it's going to be the distribution follows this, right? 1 over e to the k over t plus 1. So this is the set the distribution. It's not really monochromatic. So as I said, as an optical element, it sucks. It's really bad. I mean, it doesn't focus things at the same spot. It gives stuff all over the place. It's not, if things come at an angle, it just shifts the focal spot. It's not a great, it's not perfect by any means. But the key point is doesn't have to be, okay? Yeah.
Sorry, just to follow up on that. Is the idea to be able to detect the cosmic neutrino background?
Yes.
But I guess there's another question, which is how valid are the models that are being used to sort of describe these calculations, right?
There is no discrepancy. The index of refraction business that I talked about, it's ordinary, that there's no problem with that.
Oh, I mean the cosmological, like.
Oh, the cosmological. Look, the standard cosmology, that is the prediction. Can you mess with it? Yes. So, I mean, as I said, we are theorists. We can build all sorts of crappy models to alter this picture. For example, you can have some late time entropy dumping of neutrinos to something else or vice versa. But you have to make sure that, see, the thing is that there is a key point about neutrinos. I mean, they couple very weakly with weak interactions, but they're still patterns of the electrons. So every time you try to mess with neutrinos, you better not mess with the electrons too much either. And those interact a little bit more strongly. So there are ways to get away from the standard picture, but I'll tell you something. If there is a standard model prediction of the size of the signal, and you go there and you don't see it, boy, that's a revolution. I mean, first you will check that your experiment is not doing something wrong, but I think the standard cosmology has a very specific prediction, and that's always worth going after. Because even if it's not there, it will teach you things. Like something happened to the neutrinos, that means you have new physics, which is amazing.
Right. I mean, just in the sense that you have a snapshot of the CMB, for example, and,
Yeah.
and you're like, oh, there's some discrepancy.
Yeah, so for example, the neutrinos, strictly speaking, take our knowledge of the universe before BBN, slightly before BBN. So if we were to detect them, and we detect them in precision, right, you would need to do precision measurements to get, I'm not sure if the CMB will ever be as good as CMB, right, the ordinary CMB. That's for sure. But it's true, though, that's a fact that it takes your knowledge of the universe ever so slightly back in time. So there are things that you can check. Once we have a detection, people will find out.
So
Yeah.
Thank you.
if you don't see this and you
Yeah.
really believe it's right, do you think that they're then Majorana neutrinos?
Ah, good. That's an excellent question.
Uh,
This is what we're calculating now. So you gave me a need to start talking about Majoranas a bit. So the naive statement is that Majoranas don't give you 0. They give you naively a factor of velocity suppression, which with factors of a few turns out is a factor of 50 suppression to the signal I discussed. But there is model dependence. Turns out you can build effectively Dirac mass models out of Majorana mass matrices. For example, if you have two flavors and you don't give the neutrinos a mass through the diagonal elements but the off diagonal, it's like if you take nu mu and nu e, it's like nu e acts like a sterile neutrino for the nu mu and vice versa. So it's still a Dirac mass matrix of sorts. So there is a lot of model dependence of what the signal of how the neutrino, the Majoranas are affected, and this is something that we're working out now to understand better. The lower bound is this factor of 50 below what I talked about.
So the other thing I keep thinking about while you're talking,
Yeah.
when my mind is wandering sometimes, is how to test it. Can you use any reactor neutrinos? I mean, you show us this very beautiful picture where there's just one neutrino coming in from the left to the right, or
Yeah, but in the end, I will integrate over everything.
But everything's going every way.
Yes, exactly.
And every crazy thing, and you're
Yeah.
thinking, oh my God, I don't even want to think about it.
Yeah.
But is there something you can turn on and off? Like these neutrinos, you can't turn on and off, but reactor neutrinos go all the way down.
No,
to very
yeah,
low
but their
energies.
energy is too high. But
No,
what
but
you can do?
they're not always too high because by
No,
definition.
this is really high.
No, it's yeah, but there's a distribution.
Yeah,
Right.
if you calculate the numbers, their density is really low because it goes like the cube of the energy. We've run the numbers, like they suck, like really, like yes, you cannot take a lot of suppression. The thing you can do though is you can turn the signal on and off by, I will talk about it tomorrow, by mechanizing the structure.
Really? By doing what?
Mechanizing the structure.
This structure.
Yeah.
Mechanizing.
So, mechanizing the structure.
Oh, you can turn the effect on and off.
Yeah.
You can't turn the neutrinos on.
No,
and
the
off.
neutrinos are always there. You cannot stop them. You cannot do anything with them.
So have you done a Monte Carlo simulation where you actually have neutrinos coming from everywhere at all?
This is what I will talk about tomorrow. I haven't done a Monte Carlo simulation. I've done an analytical calculation because I cannot do Monte Carlo.
Because you can't. You need an experimentalist.
I need someone proper person to do this calculation for me. Yeah. I'll tell you, so this is tomorrow, we'll talk about the averaging, because yes, you need to take into account, this is just one stick and a very funny, very perfect thing, but of course, the neutrinos are not perfect, they're not monochromatic, they're not unidirectional, they come from everywhere. That's why we ended up with a sea-urchin, essentially. And it will suppress the signal, but it doesn't take it away. That's the bottom line.
Okay.
Yeah.
Does anybody want this?
Maybe a related question. So, is there, like, how this scheme can have an angular resolution?
Oh God. Oh, okay. Yeah.
Like,
You're asking for
if
too
talking
much
about
now.
cosmic neutrino background.
Yeah. So that's lecture. That's like probably in a couple of months because so that requires precision. And there are games you can play. Angular resolution. It's not clear. That I will have to think. I don't know the answer to that. But I mean, just to give you an idea, though, the thing is that this structure that we will constructing has a period of splits the sphere in roughly 100 parts. Okay, So that's roughly 100. Is it? Sorry, let me think. It's UWT. It's more like 10 to the 4 parts. So that means that if you look at one side, you have split up the sky to 10 to the 4 parts. So if you want to focus in one direction, I mean, you need to go, you know that you have suppressed flux from that direction by a factor of 10 to the 4. So you will need, you probably can if you have enough resolution eventually, but we are not even there yet. I mean, you probably need better than 10 to the 4 precision if you want to do, it depends on how much you want to average over the flux that come from a specific part of the sky to play these games. It won't be, the first it's like gonna be like the CMB, right? The first time they detected, all they saw is like the monopole, and it took more than 30 years to detect the dipole, the multipoles. And Kobe came, and then now we have, this is a process that took more than 70, 80 years to do.
Yeah, sure. So just at the level of concept, so it's going to be a like incomplete sphere of these rods, kind of.
So the simplest thing would be to, yeah, let's talk about, okay, it's gonna be a full sphere, but you can do incomplete sphere because it will give you a slightly different signal. It will enhance the daily or annual modulation effects. But for us, in order to we wanted to maximize the signal as much as possible, so we put the complete sphere. Okay?
Thank you.
Yeah.
Too much fun.
Yeah.
So did you try to estimate the costs, like how many sticks you need and how much iron?
I did. It's not very expensive. So that's the bottom line. So if you make it out of iron, so that's why we got excited when talking to Giorgio Gratta, and he told us about depleted uranium. Because he's like, yeah, they probably give it to you guys for free because it's junk. And if you take the depleted uranium deposits that, I mean, they don't use them. They use them in ammunitions which is not nice. So we estimate it's not very expensive to build. And it doesn't have to be the thing is that it's not a precision thing. Just need stuff. And it's not going to be expensive. Like if you were to build it out of tungsten, a 10-meter thing, I estimated it was like a few million, but.
So it sounds like theorists could make it.
Yeah, theorists can make, no, but I mean, just to tell you, by the way, this is the CNUB that we're talking about. Just to be clear, I'm not proposing this if this were a random dark matter thing, I would tell you no, it's not worth it. But the CNUB is there. This is a component of the standard cosmology. So the standards are different. Like when people do CMB experiments, they spend billions. So we need to normalize when we do small scale experiments. The reason that we make them small scales is because I mean you have a lot of parameter space. You cannot spend $1 billion for every small scale experiment. The LHC is a different issue. There was a different thing. Yeah.
No, I just wanted to say it was a very nice talk and thank you. I thought this poor man was holding the machine, and I thought I should do something with it. So okay. I'm looking forward to tomorrow's talk.
Good. Tomorrow we'll go on the details about things coming from all directions. It is what it is.
It is what it is. Thank you.
Thank you, guys.